In this video, we'll be looking at Graham's law of diffusion. So, what is Graham's law of diffusion? Graham's law of diffusion states that at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. So, at constant temperature and pressure, the rate of diffusion of a gas, which is Rho, is inversely proportional to the square root of its density. This is the mathematical representation of the Graham's law of diffusion. And this law was formulated by Thomas Graham. Thomas Graham was a Scottish chemist. He was a chemist from Scotland. So, like I said, Graham's law of diffusion states that at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. So, this law is very important, and this is the mathematical representation of this law, that the rate of diffusion of a gas is inversely proportional to the square root of its density. Rho is for rate of diffusion and D is for the density of the gas. Again, Graham's law of diffusion states that at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. So here we have that the rate of diffusion of a gas is inversely proportional to the square root of its density. So in order for us to remove this sign of proportionality, what we do is to bring in a constant. So by bringing in a constant, my rate of diffusion will now be equal to K all over the square root of D, which is the density of the gas. So my K, which is my Graham's constant, will be equal to Rho square root of D. So this is the Graham's constant for the rate of diffusion of this gas. This equation is very crucial and vital. So like I said before, Graham's law of diffusion states that at constant temperature and pressure, the rate of diffusion of a gas is inversely proportional to the square root of its density. And this is the representation of what Graham's law of diffusion is all about. So like I said, to remove this sign of proportionality, what we do is to bring in a constant into the expression. So by bringing in a constant, my Rho will now be equal to K, which is the Graham's constant, over the square root of D, which is the density of the gas. So my Graham's constant now will now be equal to Rho square root of D. So this is Graham's constant, the equation for Graham's constant. So this equation is very crucial and vital. So in a situation whereby we are comparing the rate of diffusion of two gases, let's say gas 1 and gas 2, the Graham's constant for gas 1 will be equal to Rho1 square root of D1, and Graham's constant for gas 2 will be equal to Rho2 square root of D2. According to the law of conservation of matter and energy, the law states that matter or energy cannot be created or destroyed, but can be converted from one form to another. So if we apply that law here, our K1 will be equal to K2, provided they are working at the same temperature and pressure. So K1 is equal to K2. So if K1 is equal to K2, according to the law of conservation of matter or law of conservation of energy, K1 here, which is our Graham's constant for gas 1, is equal to Rho1 square root of D1. So Rho1 square root of D1 will be equal to Rho2 square root of D2 at constant temperature and pressure. So this equation is very vital, very vital. So one thing that you must know is that the density of a gas is proportional to the sum of its relative molecular mass. That is, the molecular mass of a gas is equal to its density. As the molecular mass increases, the density of the gas will increase. As the density of the gas decreases, the relative molecular mass of that same gas will decrease. So they are proportional to each other, they are equal to each other. So if this is true, that tells us that wherever I see D, I can actually put M there, which symbolizes the relative molecular mass of the gas. So from this equation, I can get this. Remember that the density of a gas is equal to the relative molecular mass of the gas. So wherever I see D, I can actually put M there. So this is D1, it will be equivalent to M1 because they are equal. This is D2, it will be equivalent to M2 because of what? The fact that they are proportional. The density of a gas is proportional to the relative molecular mass. So this equation is also very vital. Then another point that you must consider here is that rate is the inverse of time. You must understand this fact that rate is the inverse of time. So that tells you mathematically that rate is equal to 1 all over t. Rate is the inverse of time. So if rate is the inverse of time, that means I can substitute arrow with 1 all over t. So this is the rate of a gas, the rate of diffusion of a gas, and I'm saying now that rate is equal to 1 all over t. Rate is the inverse of time. So if rate is the inverse of time, that is, wherever I see arrow, I will put 1 all over t. So if I substitute arrow for 1 all over t, or if I substitute arrow with 1 all over t, what I'm going to have is square root of d1 over t1 is equal to square root of d2 over t2. So this equation is very vital as well. This equation is very vital. Then, like I said before, that the density of a gas is proportional to the relative molecular mass. So wherever I still see D, I can put M there. Wherever I see D, I can put M there. So this is D1, it will be equivalent to M1. This is D2, it will be equivalent to M2. So this is square root of M1 over T1 is equal to square root of M2 over T2. This equation is also very vital. So in summary, we've talked of 3 basic equations as regards to Graham's law of diffusion. And these equations, they are very crucial, as most questions you will see arising from Graham's law of diffusion will involve either of these 3 formulas. So the first formula, the first equation is R1 square root of D1 is equal to R2 square root of D2. This equation is very vital. Whenever the rate and density of a gas is given, you can calculate whatever question is given to you using this formula. So the second equation is R1 square root of M1 is equal to R2 square root of M2. So when the rate of diffusion of the gas and the relative molecular mass of the gas is given, you can use this formula. Then the third formula we have here is square root of M1 over T1 is equal to square root of M2 over T2. You use this formula when the relative molecular mass of the gas is given and also the time as well. So having known this, let's take our first example. And the first example is a JAMB question from the year 2014. So the question is, a gas X diffuses twice as fast as gas Y. A gas S diffuses twice as fast as gas Y. If the relative molecular mass of X is 32, calculate the relative molecular mass of Y. So if you observe very well, the parameters that are discussed here are rate of diffusion of the gas and the relative molecular mass. So the equation that we are going to apply here will be the one that involves rate and relative molecular mass, and the one that involves that is the equation 2. So according to equation 2, we have R1 square root of M1 is equal to R2 square root of M2. So since the gas that we're discussing are gas S and gas Y, we cannot say that our 1 will be X, then our 2 will be Y. So that will be ROX square root of mx is equal to Ry square root of my. So having written this, we read again. A gas X diffuses twice as fast as gas Y. That tells you that the rate of diffusion of the gas S is twice. Twice means is 2 times as fast as gas Y. So gas S diffuses 2 times as fast as gas Y. So if gas Y is 1, the rate of diffusion of gas Y is 1, that of X will be 2, because the gas X diffuses twice. It's from this statement. A gas S diffuses twice as fast as gas Y. So if this one is 1, this will be 2, because gas S diffuses twice, 2 times as fast as gas Y. So that tells you that the rate of diffusion of gas S is 2. So instead of me to write arrow, I will now write 2. Then if you read further, if the relative molecular mass of X is 32, so the relative molecular mass of X is 32, so that would be square root of 32 is equal to the rate of diffusion of the gas Y is 1 square root of my. The question says calculate the relative molecular mass of Y. So this is what we are calculating, the relative molecular mass of Y. So having done this, our equation now will now be equal to 2 square root of 32 is equal to 1 times square root of my is equal to square root of my, because 1 times anything is equal to that thing. 1 times 10 is equal to 10. 1 times 2 raised to power 2 is equal to 2 raised to power 2, which is equal to 4. So 1 times anything is equal to that thing. So 1 times square root of my is equal to square root of my. So I have square root of my here. So in order for me to remove this square root, what I would do is to square both sides of the equation. So if I square both sides of the equation, my expression will now be 2 raised to power 2 square root of 32 raised to the power of 2 is equal to square root of my raised to the power of 2. So what I did here is that I squared both sides of the equation. I squared both sides of the equation, and the reason I'm squaring both sides of the equation is to remove the square root. So this square will cancel the square root, this square will cancel the square root. So 2 raised to power 2 is 2 times 2, and that is equal to 4 times what I have here, 32, is equal to my. Because this square has cancelled the square root, this square has cancelled the square root, leaving 32 and also leaving my. So I can actually rearrange this expression. So my my is equal to 4 times 32, and 4 times 32 is equal to 128. So this is the relative molecular mass of the gas Y. Let's look at another example. So this will be our example 2, and this example 2 is similar to the first example. The example 2 is actually a JAM question from the year 2013, and the question says the rate of diffusion of a gas Y is twice that of Z. So that tells you something. It tells you the rate of diffusion of the gas. So the rate of diffusion of a gas Y is twice that of Z. So that tells you that if the rate of diffusion of the gas Z is 1, that of the gas Y will be equal to 2, because the rate of diffusion of the gas Y is twice that of Z. So this is explainable even from our first example. So if the relative molecular mass of Y is 64, if the relative molecular mass of Y is 64 and the two gases diffuse under the same conditions, find the relative molecular mass of Z. So if you look at this question very well, there are two parameters that are discussed here: the rate of diffusion of the gas and the relative molecular mass of the gas. So what we'll do is to apply the equation that pertains to relative molecular mass and the rate of diffusion of a gas. And the equation that has that is the equation 2 of Graham's law of diffusion. And the equation is R1 square root of M1 is equal to R2 square root of M2. If we apply this equation into this question, so we will have R1 square root of M1 is equal to R2 square root of M2. So let your 1 be your gas Y and let your gas 2 be your gas Z. So that tells you that my R1 is now my RY square root of MY is equal to RZ square root of MZ. So what is the rate of diffusion of the gas Y? The rate of diffusion of a gas Y is twice that of Z. So that tells you that if Z is 1, if the rate of diffusion of the gas Z is 1, that of Y will be 2, because the rate of diffusion of the gas Y is twice that of Z. So my rate of diffusion of the gas Y is equal to 2 square root of, if the relative molecular mass of Y is 64, so if the relative molecular mass of the gas Y is 64, so my relative molecular mass of gas Y is 64 is equal to, the rate of diffusion of the gas Z is 1, because Y is twice that of Z, so this will be 1 square root of MZ, which is what we are calculating. Find the relative molecular mass of Z. So having written this, 1 times square root of M2 is equal to square root of M2, and we've explained the reason for that before, because 1 times anything is equal to that thing. 1 times 10 is equal to 10. 1 times 30 is equal to 30. 1 times X is equal to X. So we've already explained that before. So this will be equal to 2 square root of 64 is equal to square root of M2. So you can actually rearrange this expression. So this expression is the same thing as square root of M2 is equal to 2 square root of 64. So what I have here is the same as what I have here. So what I will do in order for me to remove this square root is to square both sides of the equation. So my expression now will now be equal to square root of MZ, not M2, MZ, square root of MZ, because that's our gas 2, which is Z. So square root of MZ all squared is equal to 2 square root of 2 square root of 64 squared. So what I did here is that I squared the expression. I squared both sides of the equation. So having done this, this square will cancel square root. So that will be left. We will be left with MZ is equal to 2 raised to the power 2 is 2 times 2, and that is equal to 4 times. This square will cancel the square root. So 64 will be left, so that will be times 64. So my MZ now will now be equal to 4 times 64. 4 times 64 is equal to 256. So the relative molecular mass of the gas Z is equal to 256. So this is our answer.